everybody. My name is Taylor Delk, and I work at Bryan Research and Engineering as the consulting engineer that oversees the development and support of ProMax in Canada. So, a little about myself. I graduated from the University of Oklahoma in May of 2018 with a bachelor's degree in chemical engineering, and I started working at BR&E shortly afterwards, and I've been here for about 2 years. BR&E was founded in 1974. We cut our teeth on sour systems, so sulfur production and amine sweetening. In 2005, we released the first iteration of our process simulation software, ProMax, and that has been our main focus since then. We're now on ProMax 5.0 and working on developing ProMax 6.0. We're a company of chemical engineers. If you ever give us a call to help you with a simulation or anything like that, we'll get a chemical engineer on the phone very shortly. We're happy to build models for our clients. We're happy to give you process support, simulation support, technical support. We try to pride ourselves on that. Now let's go ahead and start talking about acid gas injection. So this will be the agenda for what we're talking about today. We'll look at the process overall. We'll look at the solubility of water in acid gases, which directly feeds into preventing hydrate formation in these acid gas injection systems. We'll talk about the proper thermodynamic packages to use when you're modeling these systems, and then we'll go ahead and show a little bit of the modeling itself at the very end. So first, let's consider where are these gases coming from. Normally, your acid gases are going to be coming from your amine units. So you used an amine unit to sweeten whatever hydrocarbons you're going to be selling. Now you just have these acid gas streams, and you have to find somewhere to put that. So there's two options you have here. You can do sulfur recovery, where you process the sulfur into a pure elemental form and then try to sell that. Or you could do acid gas injection, where you say, I'm not going to get anything out of this. Let's just pump it back down into the ground and forget about it. Coming off of those amine regenerators, we're going to have a low pressure, high temperature acid gas, some combination of H2S and CO2. With the acid gas injection system, it's a little bit easier and cheaper than SRUs. There will be no emissions, whereas sulfur recovery units can still emit non-sulfur components, so CO2, things like that. With the acid gas injection, you won't be able to recover any product or waste heat like you can with the SRU, so a little bit less able to integrate with your whole process. It's a pretty common option that people go with. SRUs, I think, are becoming a little bit less common. Let's go ahead and take a look at the overall process flow. You have your acid gas coming in, some combination of trace hydrocarbons, a little bit of nitrogen, and then mostly H2S and CO2. So you do have to consider with those trace hydrocarbons whether or not at any point in this system you'll form a hydrocarbon phase. Not likely, but something to keep an eye out for. You can see there's three components to this, just compression, pipeline, and injection line. So coming off of that amine regenerator, we're going to be at low pressure again. We need to get that up to a high enough pressure that we can inject it in the reservoir. So we have a compression system with cooling, separation, pipeline to ship this acid gas where we need to inject it. And then, of course, the injection line, buried wellbore that's going to take this acid gas from the surface all the way down to the reservoir where it needs to go. So we briefly touched on that non-aqueous phase behavior, figuring out with this system if you're going to be forming a non-aqueous phase. We'll try to avoid that probably. We're going to need to look at that water content that feeds into the hydrate formation. If we form solid hydrates anywhere in this system, it's going to either rip up our equipment or make it a lot harder to get that acid gas down to the reservoir. So if we're forming hydrates in our pipelines, you're effectively restricting that flow and making your compressors work harder to get your acid gas where it needs to go. It is important to point out that this acid gas is usually going to be pumped down into a different reservoir than the one that it came from, which is part of why this pipeline is definitely necessary. You can pump it back down into the same reservoir, but odds are that's going to be increasing your acid gas content of whatever you're producing. So when it sees that amine unit again, it's going to be a little bit richer in acid gas, and it's possible it will overload that system over time. Because we're dealing with these high pressure acid gases as well, we're going to be using pretty much all stainless steel in this compression system that protects the equipment from corrosion and anything like that. So about the compression itself, we are going to have a high compression ratio, sometimes greater than 50. Again, that's because it's coming off that amine regenerator, very, very low pressure. That reservoir way underground is obviously going to be very high pressure. So we're going to need at least 3 to 5 stages on this system. If you try to keep the stages lower, then your compressor outlet temperatures are going to be a little bit too high. Your compression efficiency is going to be a little bit lower. Trying to compress a hot gas is a lot harder than trying to compress a cooler gas. And then, of course, with the temperature restrictions, we want to make sure that we keep it 5 degrees above the acid gas dew point, and that's to keep acid gases from leaving in this liquid phase. And we want to keep it 5 degrees above hydrate formation, of course, because that's never going to help us to have solids in this compression and pipeline system. So coming off of each compressor, you do have that cooler to keep those temperatures in line. When it cools down, you do have water dropout. There's trace amounts of acid in that water, but the water is going to come out of the system. We don't want to be sending liquids to our next stage of compression. And also it just frees up some space in the system. That's why we have that. And of course, we have the multiple stages to keep those temperatures where they need to be and to keep the efficiency of the process high. With that water removal, you'll also get some protection from hydrates. If you have less water in your system, it's going to be a little bit harder for those hydrates to form. And of course, that's going to help us down the line with the pipelines and injection as well. So we can actually optimize this system to try to get the most water dropout that we can. And we'll be looking at that a little bit later. The lowest temperature that you're going to be seeing is probably going to be around this wellbore. So when we do look at hydrates, that's where we're going to want to focus. Another way to avoid those hydrates is to apply heat before going to the pipeline. So some form of line heater could keep that lowest observed temperature higher than that solid formation temperature and keep you from forming those hydrates just based on the operating temperatures you're working with. Another way is to remove that water naturally, like we were just talking about with this liquid dropout system. If that's not enough, you might have to put a dehydration facility in here. That could be a mole sieve, it could be a glycol system, whatever is most applicable there. And then finally, you could use inhibitors. So ethylene glycol is going to keep those hydrates from forming and depress that solid formation temperature, and then it can just go down into the reservoir with everything else. Methanol is another one you can use, but it's important to note that if you do use methanol, you're going to want to model this using a polar package. So Ping-Robinson polar, SRK polar, something like that. Methanol is a highly polar molecule. It's going to throw off your results if you try to model it with just a normal property package. So we talked about optimizing that compression system to drop out some water, maximize that water removal rather. This is what you would want to look at when you're considering your operating pressures coming out of your compressors. Here on the left, we can see the difference between high H2S systems and high CO2 systems. CO2 tends to carry a little bit less water with it. H2S is going to be a lot more accepting of water in that gas phase. So there is considerations to be made there in terms of what pressures you're going to be running at. You can see it dips down and then comes back up after a little bit. So you can design your system to really get all that water out if you're looking at it. Similarly, on this side, you can see the effect of those cooler temperatures. So the colder you are, the more water you're going to drop out based on these equilibrium calculations. And then this is just a little bit of verifications of our data. So we have the GPSA data for water content of saturated CO2. That will be the dots, and these are at different temperatures based on the color. And then the lines are going to be the ProMax predicted data at different colors with different temperatures as well. But you can see that we're matching that data pretty well. And the same story with H2S over here. Dots are going to be GPSA, lines are going to be ProMax. And you can see that we come pretty close on all of that data. Just a little bit of verification to show that we should be predicting the right water dropout, and things like that. So this is just a picture of what the operation is going to look like. We're going to start at high water content, compress a little bit, and then We're going to cool down and drop out some water. That's going to be the separation part of the process. We're going to compress again, cool down, drop out some water, compress again, cool down, drop out some water, compress, cool down. And then finally, when we inject, we're happy to just cross right over that saturation line and start producing acid gas liquids. At that point, it's not going to be affecting our process to form those liquids. It's only going to help us push that material down into the reservoir. With the higher pressure and the higher density that comes with those liquids, it makes it a little bit easier to get that hydrostatic head effect, pushing all that material down into the reservoir. At no point do we want to be forming acid gas liquids until we get to injection. This is just a similar graphic showing operating data. So we can compress, cool down, compress, cool down. What we're going to be doing is making sure we avoid this maximum temperature based on the equipment we're using. If we have high pressure, high temperature acid gas, this is around the temperature that we want to be afraid of for our equipment. We have the hydrate line here. This is going to be based off of the final stage of compression. Why is that? Well, you do want to look at hydrates all throughout the system, but we talked about the lowest temperature is going to be experienced at your wellbore. And so that's going to be after that final stage of compression. So that's the one we really want to be careful about. We don't want to be forming hydrates in our pipeline. We don't want to be forming hydrates anywhere, but you can usually get away with just looking at this final compression stage composition. As that water drops out through the stages, this hydrate curve will move. So if you are interested in looking at that, you can put hydrate analyses on all of those streams. This minimum temperature line that we try not to cross until the very end is going to be based on forming those acid gas liquids again. So you can see it kind of parallels that liquid line on the phase envelope. That's because we're just trying to stay about 5 degrees above that. So it makes sense that it is a similar curve. And finally, when we inject into the wellbore, our pressure rises quite a bit. We cross right across that liquid line, don't care anymore. It's going to actually help us with that injection. And then you can see pressure goes up as it gets to the reservoir. Finally, let's talk about what thermodynamic packages we want to use for this. Normal equations of state are fine, Ping-Robinson and SRK for the vapor phase. When we're looking at the liquid density method, we want to be using an equation of state because these gases, once they get up to that high pressure, are going to be supercritical, but they're also going to be low density liquids. So kind of confusing. ProMax just assigns a phase when you're supercritical. It doesn't have a supercritical phase designator. So it's going to say, if you're operating right here, I'll say you're a liquid. If you're operating right here, I'll say you're a vapor. But in effect, there is no difference once you're supercritical. That's why we want to use the equation of state for that liquid density method instead of the normal Costald. So when you set your environment up, be careful with that. You can see here that all of the equations of state are pretty similar, even in the supercritical region up to about 100 bar. And that's when they really start to diverge. So there are more effective equations of state depending on what your final outlet compressor pressure is going to be. And so you would want to pick based on that, but effectively they should be the same up until 100 bar. All right, if you do want to give us feedback on that, we have a link here. You can also tell us other things you'd like to discuss, but we're going to go ahead and move on to the modeling portion of the webinar. You can see here we have a similar flow sheet, but I want to point out a couple of things. First, we have combined the coolers and the separators here. On the other flow sheet, you had what looked like a fin fan cooler before the separator. To keep things simple here, ProMax lets you just attach a Q stream straight to that separator and kind of make the flow sheet a little bit smaller. So when we do define these separators, we'll have to give it some kind of temperature specification. You can see that here with the 50 degrees C, as well as some kind of pressure drop specification. So a little bit different than what you might be used to, but it can make things a little bit simpler for you. We're going to be targeting 138 bar gauge for our reservoir pressure. If you were designing this system, you would know what that reservoir pressure is. And so you would want to design this compression system to be able to reach that reservoir pressure when it gets down there. If you go lower than that, your injection system is not going to work. If you go higher than that, you're just going to be wasting compressor power up here. Our environment here is predefined, so we won't have to mess with that. Our phase envelopes are going to be on a dry basis. The reason for that is that we're not super concerned about when that water starts to drop out. We know it's going to be dropping out throughout the whole system. What we're really concerned about is when that first drop of acid gas starts to condense. We don't want that to be happening until we get down to the injection line. And when that does happen, it's actually going to help us. That higher density liquid or supercritical fluid is going to be pushing down on that hydrostatic head effect through the wellbore. That's going to give you the pressure increase you want to go down to the reservoir. And so if we can get liquid forming here, it's going to take a little bit of the pressure off of the compressor system to compress it up to that reservoir pressure. So the higher density will push down harder, and that'll help us out. All right, so let's go ahead and get simulating. First, I'm going to go ahead and specify these pipelines. So you can see the Q streams attached. What that's going to be letting us account for is the heat transfer with the ambient surroundings. If there is no Q stream on a pipeline, you can still account for hydraulics, but you're not going to be able to account for that heat transfer, which is going to affect your hydraulics. So this first pipeline, I'm going to say that it is 1.6 kilometers in length. So this is a consideration with your acid gas injection systems is where's the nearest reservoir that I can pump this into? If I can't, I might have to find some other kind of system to deal with my acid gas. We're going to say that it's just a flat pipeline with no elevation change. Schedule 80 with a nominal pipe size of 2 inches. Our outside temperature is going to be 20 degrees C. Our material of construction is going to be carbon steel. And putting in all this heat transfer information is going to let us predict the heat transfer coefficient and then get that heat transfer information, predict liquid dropout. We are in a buried pipe surroundings. We're going to say that it's buried about 1 meter. We're going to say that we are operating in wet clay. And now you can see it's pulling in information for ground thermal conductivity. When we execute this part, we are going to get a heat transfer coefficient predicted. And we're going to go ahead and do the same thing for the injection line. So for the injection line, we're going to actually give it 10 segments. This is going to give us a little bit more granularity in our results. And it's going to break up the calculations into shorter increments. So what we get for that is a little bit more accuracy and a little bit more granularity. Elevation change should be 0.16 or negative 0.16 kilometers for all of these. I'm going to show you a different way to specify this. I'm going to copy to bottom so that elevation changes are removed. And you can see the inclination angle opened up for us. So if we're going straight down, our inclination angle should be negative 90 degrees. And you can see it's now populating the elevation change for us. Our pipe schedule is still going to be 80. Our nominal pipe size is still going to be 2 inches. And we're done there. Now we're going to go over to our heat transfer information and do the same thing we did just a moment ago. There is going to be a little bit of a difference, I guess. So on the ambient temperature, what we can do is we should expect a temperature gradient, right? If we're going 1.6 kilometers under the earth, we'll start out at 10 degrees C. We'll go to 13.75 degrees C. And ProMax recognizes the pattern we're going to go with and just populates that temperature profile for us. For material construction, again, we're just going to say it's some type of carbon steel. Now, instead of buried pipe, we're going to say buried wellbore. That is going to change these calculations. So you can see there's different correlations for different types of piping. The ground we're still going to say is the same, wet clay. And now the well flowing time, we are going to need to populate. Well flowing time is going to account for the transient nature of this heat transfer, right? When you first start flowing this acid gas down into the ground, it's going to be either heating up or cooling down the surroundings. I guess, let's see this temperature, 10 degrees C. It's probably going to be coming in at 50 degrees C. So it's probably going to be heating up the surroundings at first. After a while, you would think that that would reach steady state. So this is a way of accounting for how close to steady state that heat transfer is going to be. You can see the calculations here, what correlations it's based off of. But that is effectively how we specify these pipeline systems. Now, this system is not yet ready to execute. You can see that we have a maroon stream here for our acid gas. What that means is it can be calculated, it can be populated with a temperature, pressure, composition, and flow that we need to fully define a stream, but it just hasn't been yet. So if we hop back over to our feed page, you can see that we had some kind of dry gas analysis on our acid gas, and we put that in there. But clearly, if we're coming from an amine regenerator, we would expect to see some water there. So what we did was we set up a saturator block with water to give us a more accurate feed for our compression system. And now you can see this is green, this is fully defined, fully calculated temperature, pressure, composition, flow, but our compressor is not yet ready to calculate. So what are we missing? Well, first we're going to need some type of efficiency. The efficiency of this compression process is going to help us figure out the outlet temperature. And of course, we need to know some kind of pressure specification on the outlet, right? What are we trying to achieve? Most compression systems have a ratio, a compression ratio of around 2. So we can start with that and see what that gives us. Okay, so we're fully defined here. You can see we got quite a bit hotter, and now we're going to be doing that cooling down and dropping out of that water. So we'll go with 50 degrees here. And we'll put a pressure drop in here of 0 bar. All right, so we've seen how to do these. We actually had something set up in here already to auto-populate the rest of this. You can see here a advanced specifier on the compression ratio for compressor 2, 3, 4, and 5. All this is doing is saying, hey, whatever the compressor ratio is here, make it the ratio all the way down the line. And of course, since we are probably using air coolers and trying to achieve something close to ambient, all of these outlet temperatures are going to be around 50 degrees C. Keeping in mind that we're modeling a cooler and a separator with this single block. And it looks like, because everything's turned from bright red to maroon, we should be able to fully solve and converge this simulation. So let's go ahead and do that real quick. So you can see we have an analysis here that's calculating our hydrate formation temperature at 27.3 C. We're a little bit below that, and ProMax is automatically checking those streams and letting us know. So we'll look at that in just a minute, see if we can get that to go away. But there's something else to notice here. We aren't anywhere close to our reservoir pressure. If you started this system up in reality, you're not going to be injecting any acid gas into that reservoir. We need to make sure that we design it in such a way that it hits that. What variable can we play with to do that? It would make the most sense to play with that compression ratio that we had just set up, right? So one thing we can do is we could go here and go 2.5 and see if that gets us where we need to be. And that might be a little bit too high, so we might go back down to 2.4. And we can do that guess and check process a few times until we get pretty close. But there's an easier way to automate that in ProMax. So what we're going to do is set up a simple solver. So this is ProMax's method of guessing and checking for us. I put that solver on that compression ratio for compressor 1, and compressor 2, 3, 4, and 5 are all going to update to go along with that. I'll call this solver compression ratio solver, just so I know what it is later. And I'll say we want to come up with an error function for this iterative process to iterate on, right? A little guess and check. It wants to drive this function to 0. So every time that this simulation executes, it's going to look at this equation and say, is it 0 yet, or is it within 0.0001 of this? And then if it's not, it'll execute again. If it is, it will say that the simulation's finished. Let's just start with an algebraic equation to say this is what we want. I want my reservoir pressure to be equal to 138 bar G. ProMax has already rearranged this inside this box. It wants it to be in the form of reservoir pressure minus 138 bar G is equal to 0, right? This looks a little bit more like an error function. And then ProMax has already taken care of that equals 0. So what we're left with is our error function respress minus 138. But ProMax doesn't automatically know what that respress means. I know that it's the pressure in P stream 18 reservoir. So what I have to do is find that. I know it's on a flow sheet. I know it's on the acid gas injection flow sheet. I know it's a P stream. And here we found it. Pressure is a phase property of the total phase. And you can see here that ProMax is saying, I know what you're talking about. Now I just have to say that the name of this variable is respress. So when it looks at that error function, it goes here, finds that, compares it to 138, and decides whether or not it needs to iterate again. So this should be good to go, right? One note is that we do need something to start iterating on. So it's good that I have this calculated value of 2 from when I put that compression ratio in earlier. And now we can just see ProMax do some guessing and checking. One thing to note, I'm going to go ahead and stop it, is that on these solvers, ProMax's default tolerance is going to be 0.001. So it's trying to get within 138.001 bar G or 137.999 bar G. I'm not too worried about it being that close. So what I'm going to do here is adjust the weighting. All the weighting is going to do is it's going to take that residual error from the error function. It's going to multiply it by this weight, and then it's going to compare it to our default tolerance of 0.001. So if I say 0.1 here, and I'm already within 0.01 of 138 bar G, it's going to multiply it by 0.1 and get me 0.001. And so instead of iterating again like it normally would, it'll say, you know what, that's fine. I'm not worried about it, and it'll move on. I'm actually going to make this 0.01. So let's see if it solves a little bit faster now. And there we are. And it's at 138 bar G. So maybe I didn't need to change that, but 138.006 would have been outside of that tolerance. So loosening that weighting did help us there. So we made it to our reservoir pressure. Let's look at our solids formation now. That's awesome. We're now above our solids formation temperature. We probably dropped out a little bit more water with those higher compression ratios. Instead of 2, we're now at 2.09. So higher pressures, same temperatures, probably means we dropped out a little more water on the way, and that's why our solids formation temperature is a little bit lower now. All right, so that is the basics of modeling an acid gas injection system. If you have any questions, give us a call at 979-776-5220. Have a great day. Thanks for joining us. Bye-bye.